Hi everyone, today we're going to be counting the pages of a book. Let me tell you what the general problem is that we'll be dealing with. Let's suppose we have a book and we flip to a page, let's say page 10, and then we flip several pages ahead, let's say to page 40. The question is, how many pages are there in between? Inclusive, so including 10 and 40, or exclusive, excluding 10 and 40. These are related problems, but we're going to solve them separately and then see the connection. Now, usually in my experience, students jump to saying the answer is 40 minus 10, which is equal to 30. And this isn't bad as a first guess, but it is wrong. So let me show you how to solve this properly. The way that I do it is that I wouldn't actually list out all the pages, but I would make a list in shorthand like this, 10, 11, 12, all the way through 40. And the idea is to use transformations, use bijective transformations to get something that looks like 1, 2, 3, all the way through n for some n. And then you'll know that the answer is n because you're counting 1, 2, 3, all the way through n. So let's see what transformation we can use here. What we're going to do is subtract 9 from each of the entries, and that gives us 1, 2, 3, all the way through to 40 minus 9 equals to 31. And so the answer is 31, which is 1 off of our guess over here. Now we've tackled the inclusive problem. Let's look at the exclusive problem. In this one, our list is the following. We don't start with 10 because we're not including 10. We start with 11. We have 12, 13. And we don't end with 40, we end with 39 because we don't include 40. Now the idea is to do the same thing, to subtract 10 from each entry, which is 1 less than this over here, 11. And we get 1, 2, 3, all the way through to 29. So the answer is 29 because we've counted 1, 2, 3, all the way through 29. Now, this should make sense because 29 is equal to 31 minus 2. And this minus 2 is represented by 10 and 40, which we excluded. So that's just a little double check for us to make sure that our final answer over here was correct and that it relates correctly to our answer over here. Let's generalize this idea because so far we've dealt with concrete numbers. Let's see if we can generalize this to other kinds of finite sequences. Now there are two restrictions that we're going to need. One, the initial entries must be distinct, and 2, the transformations that we use at each step must be bijective. What the second condition ensures is that at each step the entries the entries remain distinct. And if you're familiar with bijective functions, that should be clear. So I'm gonna show you how to do this for two general types of sequences. One is an arithmetic sequence, and the other one is a geometric sequence. So let's see how these look in general. The arithmetic sequence looks like this: a plus nd, a plus n plus 1d, all the way through a plus md, and this n and m have to be integers, where the a is the initial term and d is the common difference, for those familiar with the terminology of arithmetic sequences. And the geometric sequence looks like the following: br to the n, br to the n plus 1, all the way through to br to the m. And once again, n and m have to be integers. And remember, there are restrictions on a, d, b, and r, because we're requiring that these sequences have distinct entries. And we'll get into exactly, I wouldn't say exactly, but we'll get into some idea of what those restrictions are as we go along using bijective functions. So let's see what we can do here. Arithmetic. What we'll do first is let's write out the sequence again. A plus nd, a plus n plus 1 times d, all the way through to a plus md. First, we're going to subtract a. So from each term, so we get nd, n plus 1 times d, through to md. And this was bijective. Now what we'll do is that we're going to divide all the terms by d. And this is okay because d is not equal to 0. Why isn't it equal to 0? Because if d were equal to 0, then all the terms would be equal to a, and then they wouldn't be distinct. So we can assume that d is non-zero, and that gives us the sequence n plus 1 all the way through to m. And finally, we're going to use the trick that we used with the pages of the book, which is to subtract n minus 1 from each term, which gives us 1, 2, all the way through to m minus n minus 1. And this term over here is simply equal to m minus n plus 1. So that's the number of terms in the sequence. Let's move on to the geometric sequence now. The sequence, we'll rewrite it: br to the n, br to the n plus 1, all the way through to br to the m. First, what we're going to do is divide all the terms by b, which is non-zero. And notice that b has to be non-zero, otherwise all the terms would be 0, and that would make the terms non-distinct. So it has to be non-zero. We get r to the n plus 1, all the way through to r to the m. Now what we're going to do is divide all the terms by r to the n minus 1. And this is okay because r is also non-zero. If it were 0, then we would have multiple terms that are equal to 0, and that would be unacceptable. So we get r to the 1, r squared, all the way through to r to the m minus n plus 1. And now we just count exponents. Formally we're using a logarithm, but it suffices to just look at the exponents since they're all distinct. 1, 2, all the way through to m minus n plus 1. So the answer is m minus n plus 1, which is interestingly the same as the answer that we had up here for the arithmetic sequence. Let's do a quick recap of what we did today. We started with the example of counting the pages of a book from page 10 through page 40, and we distinguish between two problems. One is the inclusive problem and one is the exclusive problem. We found that in the inclusive case the answer is 31, which does not equal 30. 30 was the initial guess that most students make. In the exclusive problem, we found that the answer is 29, which is 2 less than the answer in the inclusive case. We stated 2 general restrictions on the problem and on the method. One is the restriction on the problem is that the initial entries have to be distinct. And the restriction on this method for it to work is that the entries at each step have to remain distinct, which is given by the transformations at each step being bijective. And finally, we applied this idea to arithmetic sequences and geometric sequences. We found that in the arithmetic case, the answer is m minus n plus 1. And in the geometric case, we found that the answer is identical. It is m minus n plus 1. Okay, thank you for watching, and I'll see you next time.